let there be light, and quirky quantum surprises. In the early 1900s, a band of tinkerers and engineers set out to perfect the humble light bulb. They knew that a glowing filament was simply a filament heated by an electric current, but they had no idea why the light's color shifted as the filament got hotter. Up to a point, things seem straightforward. As you crank up a hand-powered generator, the light grows brighter, and its color moves from red to yellow. Yet, no matter how hard you try, that cool blue part of the spectrum remains stubbornly out of reach. Even the sun, with all its heat, hardly emitted any ultraviolet light beyond blue. Enter Max Planck, who puzzled over why hotter filaments changed color. When a beam of light, split by a prism, revealed a rainbow of hues from red to violet, scientists were forced to wonder, what's really going on inside that incandescent filament? To push the mystery further, Planck's team built a contraption with spinning disks that could generate enormous voltages. Sparks leapt between metal spheres like something out of a mad scientist's lab. Oddly enough, shining a strong light on these disks made the sparks jump even more easily. Clearly, light was doing something bizarre with electricity, and the answers weren't hiding in plain sight. At the time, light was thought to be nothing more than a wave, a notion supported by the beautiful rainbows seen in soap bubbles and oil slicks. The idea was simple. Just as ocean waves pile up and crash, maybe more energetic waves could knock electrons loose and produce higher voltages. But experiments soon threw a curveball. It turned out that intense red light barely budged electrons, while feeble blue or ultraviolet light did the trick immediately. Something wasn't adding up. In 1905, Albert Einstein stepped into the picture with an audacious idea. What if light isn't just a continuous wave, but also a stream of tiny bullet-like particles called photons? In his view, these quantum packets of energy came in different sizes. Red photons carried little energy, like feeble BB pellets, while blue photons were more like high-energy billiard balls capable of knocking electrons free from their metal prisms. This radical rethinking ignited a fiery debate. How could light be both a wave and a particle? The puzzle was as confounding as it was thrilling, setting the stage for a clash of the greatest minds, most notably the Danish genius Niels Bohr and Einstein himself. Fast forward a couple of decades to the mid-1920s at Bell Laboratories in New Jersey. In a mind-blowing experiment, scientists fired a beam of electrons at a crystal and watched their scattering pattern. Instead of behaving like solid marbles, the electrons created an interference pattern, a hallmark of waves, as if they were passing through two slits at once and interfering with themselves. Imagine tossing a coin so fast that it seems to show both heads and tails simultaneously. Only when you catch it does it decide on one outcome. Bohr suggested that until we measure it, an electron is in a state of indecision, a probability cloud of possibilities that only collapses into reality upon observation. But here's where it gets even more surreal. In the quantum realm, the very act of observing a particle isn't passive. It changes the particle's behavior. Unlike the macroscopic objects we see every day, quantum entities only choose a state when we interact with them. To Einstein, this was preposterous. "Does the moon disappear when I'm not looking?" he famously quipped, arguing that reality shouldn't depend on observation. The plot thickened with the discovery of a bizarre quantum phenomenon known as entanglement. Imagine two coins spun by the same cosmic toss, sent off in opposite directions. According to quantum theory, these coins remain mysteriously linked. If you eventually check one and it shows heads, the other will instantly be heads too, no matter how far apart they are. Einstein dubbed this spooky action at a distance, insisting that the coins' fates must have been sealed long before we peeked, like gloves already sorted into left and right pairs. This debate, are particles predetermined like Einstein's gloves, or do they come into being only when observed, as Bohr claimed, was not just philosophical musing, but the heart of quantum mechanics. Einstein argued for an objective reality that exists whether we look or not, while Bohr maintained that the very act of observation brings reality into being. Years passed, and though the intellectual battle raged on, practical applications of quantum mechanics began to flourish. The technology spawned by quantum ideas transformed electronics, communications, lasers, medicine, and even nuclear power. The practical successes led most working scientists to adopt the motto, "Shut up and compute," putting the philosophical debates on the back burner. Then came John Bell in the 1960s, a man determined to settle the quantum brawl once and for all. Bell devised a thought experiment and later equations that could test whether Einstein's preset particles or Bohr's measurement-made reality was correct. His idea was akin to a high-stakes card game. Imagine a dealer who shuffles a deck of cards so sneakily that the outcome is hidden until you decide the rules after the cards are dealt. In this game, you win or lose based on whether the two cards match. John Bell argued that if the cards, or quantum particles, always came out matching more often than chance would allow, regardless of when or how you set the rules, then the particles must have been predetermined, like Einstein's gloves. But if they didn't, then the mysterious nature of quantum mechanics, where outcomes are only decided upon observation, would be vindicated. At first, Bell's ideas were largely ignored. That is, until a group of unconventional physicists at the University of California, Berkeley, hippie scientists with a taste for LSD, deep conversations about Buddhism, and a keen interest in the weirdness of quantum physics, decided to test Bell's predictions. Using clever setups with lasers, crystals that split light into entangled photon pairs, and detectors that measured their polarization, think of it as a suit in our card game analogy, they ran the experiment. When the laser fired and the photons danced through the apparatus, the results were astonishing. The behavior of the entangled photons did not align with the idea that their properties were predetermined long before measurement. Instead, their characteristics seemed to pop into existence only when observed. The experiment supported Bohr's view of a reality that is not fixed until measured, leaving Einstein's insistence on an objective, observer-independent reality in the dust. This experimental vindication of Bohr's ideas shook the foundations of physics. It confirmed that at the quantum level, reality is a far more elusive and interactive game than we had ever imagined. The particles are not secretive messengers pre-deciding their actions. Instead, they are dynamic players whose properties become real only through interaction. The saga of light, electrons, and quantum conundrums is a wild ride through the frontiers of science, a journey from the early tinkering with light bulbs to the profound mysteries of quantum mechanics. Along the way, brilliant minds like Planck, Einstein, Bohr, and Bell challenged our notions of reality, showing us that at the tiniest scales, nature is as enigmatic as it is exhilarating. In the end, the story isn't just about disproving or proving a theory. It's about embracing the wonder of a universe where even the act of observation plays a starring role in creating reality. And perhaps that's the most exciting light of all, the spark of curiosity that continues to illuminate the quantum world.